Okay, so the next lecture is going to be given by Carmen. Carmen is, of course, one of the co-organizers of this meeting and needs no introduction as such. She is a professor at University of Leeds, Department of Applied Mathematics, and she's going to talk on stochastic birth and death processes in immunology.
Thank you. Can you hear me? Yeah. So I will actually give a talk that it's a combination of two, but given that I have a whole hour and given that the aim of this first bit of the meeting, which is the workshop, is to give you a flavor of maybe something more hands-on, I thought in order to introduce the work that we've been doing at Leeds in mathematical immunology, to give a background on the mathematics behind it. So I would go, I mean, not very fast, but relatively quickly, through the theory of Markov processes with a focus on birth and death processes that can be characterized by having an absorbing state in general, and that would lead to understanding times to extinction, for example, in the context of immunology. I know that there's been a few talks in which this concept of extinction has come up. And I would like to say that this is work that was pushed by our PhD student, Emily Stirk, and it's nice to see that, in fact, she's now working for the NHS in England, helping with the development of some mathematical and statistical modeling. So anyhow, that's the outline, and please don't hesitate to ask in the middle of the talk. So I'll give a general theory. I mean, I'm not going to cover in an hour everything about continuous time Markov chains, but just to give you a flavor. So just for the purpose of references, there's a very nice book by Linda Allen, An Introduction to Stochastic Processes with Applications to Biology. She also has another book that's more focused on deterministic modeling. So if you've really never been introduced to stochastic processes, that's a very easy way, if you're not an applied probabilist, and I'm not, to get introduced to the field. And then the other references from which I'm going to draw the immunological work at Leeds are also given there. So what is it that we want to model? So let's suppose that you want to try to understand the dynamic or the time evolution of a population of cells. So in that case, your natural variable is the number of cells that in this case I've called x of t, and t is a continuous variable measuring time, but the number of cells, my variable, is a discrete variable. So this is what is a continuous time Markov chain, where you have your random variable that can take values in a certain subset of the real line, in this case, the integers and positive integers and 0, and we can have different types of stochastic process depending on whether I have an infinite set of space or I have a maximum number, capital N, of possible states in my system. So for example, if I know I've never seen any more than n cells. So important to put first is to phrase what we mean by a Markov process, which I think really gives the flavor and the characteristic of how the systems behave, and that is the Markov property. So very simply put, if I have a number of time events increasing in order from t0 up to a final tn, and I ask myself, given that I'm observing at a later time, tn plus 1, given that I know what happened to the system at previous times, in principle, you may wonder that, of course, to know what's happening at a later time point, I may need to know exactly what happened at any of those previous times. So the Markov property is very reassuring, and it tells me that in order to predict the future, I only need to know what's happening right now, and I can forget about what happened before. And as you can imagine, that is a lot of sort of baggage that one can get rid of, which is nice and makes it easier. So this is essentially what the Markov property tells us, and very nicely what I'm going to show is that based on this Markov property and a number of other properties would follow. So what we would be interested in understanding for our models is, given my random variable, whichever property of my system that I'm looking at, I want to know, at a given time, what is the probability to be in a given state? What is the probability to have n cells or 0 cells? And important, and of course I'm being very, very casual, I'm not, as I've said, I'm not an applied probabilist. What we'll see that we'll need for our model development is that we need to understand from a biological perspective how I can define what I will require, which are the transition probabilities. If I know I'm in a given state at a certain time s, so if I know I am in I at time s, what would be the probability to be in a different state, or not necessarily different, another state j at a later time t. So for that, that is what I have said, transition probabilities, and in principle, I have 2 time points, the initial and the final. So when I restrict myself to the case in which it doesn't matter what is the initial and the final point, but I'm only interested in the difference, how long I take to make my transition, then I introduce what it's called a homogeneous or stationary transition probabilities. And for the purposes of what I'll be presenting today, this is the types of stochastic Markov processes that I'll be looking at, those that are stationary and homogeneous. So then with that, my transition probabilities form a matrix, and of course properties of these transition probabilities, they are all greater than 0, so positive or 0. And what we know is that if I fixed my fiducial state I, and I go over any possible transition to state j at any given time, and I add them up, that of course needs to be 1 at all times. So that's just conservation of probability. And the probability that there is a transition from a state I to some other state at time t equals 1. So that would be important. And so the question is, given these rules, how can I then put this in place to understand the evolution of the system? So there is a very simple theorem, but at the same time I think, to me, that's sort of the beauty. It's one of those theorems that gives you properties that can actually make you quantify things. Sometimes certain theorems are only sort of proof of existence or uniqueness, but in this case, it actually tells you how you need to do things, and you can implement what I'll be describing just now in terms of Gillespie algorithm. So I'll also talk about that later. So the idea is, if I know my transition probabilities at time t, then what can I say of what's happening at a little bit later delta t? So for example, if I know I'm in state I at time 0, what is the probability to be at a little bit later than t plus delta t, the probability to be in j. So what one can actually show is that these probabilities can be recovered from only the transition probabilities that I've just introduced here, and the probabilities, the transition probabilities at the previous time t. So the proof is very simple. I have it here. So it's just basically 3 lines. So the idea is, if I know at an initial time I'm in a given state, how do I know I'm going to jump to a different state in time t plus delta t? So that, by definition, is, you can say, well, sometime in between, I've jumped to some in-between state, which I'll call k, and of course it's going to be in my state space. So that is this transition probability, where I'm summing over k. And given the definition of conditional probability, and of course it's a Markov process, I can rewrite it like this. And with the Markov property, given that this transition is earlier than this one, I can forget about that initial condition. Then I can recover this term as the transition probability in a very small time interval, and I have obtained the forward Kolmogorov equation. So, as I've said, it's sort of a formal theorem, but at the same time, this will allow me then to work things numerically, and of course, pencil and paper when I can. So for the students, and for those that maybe not be so familiar with stochastic processes, I'm giving you a bit of homework to show the backward Kolmogorov equation. So what is a birth and death process? So a birth and death process is nothing else but a very special type of Markov processes in which the transitions take a peculiar or particular form. So transitions in this case are allowed as follows. So if I am writing here 0, 1, 2, 3, my my possible states, a birth and death process is a Markov process in which I only have transitions between nearest neighbors. So I can only jump from state n to n minus 1, and that's a death, of course, because if I have a population of n individuals and in a very small time interval I have a death, I go down by 1 with rate mu n, and I can go up 1 with birth rate if I have n individuals and there is, for example, an event which is a cellular division. I increase my population by 1 and I end up in n plus 1. So, of course, I can go up or I can go down, and in principle, so when I get close to 0, I can have one individual, and if that individual dies, I end up in 0. And notice that 0 is already a special state, and depending on the type of process that I am considering, I am able to go from 0 to 1, sometimes yes, sometimes no. So, for example, if there is migration into my population, at some point, right, someone may die, but then someone just may happen to join the population from a different compartment, and I can jump. But then there be circumstances in which lambda 0, the probability to get out of 0 just because there's an increase in 1 unit in your population, might be 0. And in that case, if this rate to get out of 0 to 1 is 0, you are stuck in 0, and 0 is actually called an absorbing state. In the case when my population is finite, of course, if I can only go up to a given maximum number of states, just because my population will not grow some imposed, or just because there's some carrying capacity that doesn't allow me to grow any larger, then what you need to know is that when you get to n, you cannot get out of n, and you go down, and of course n in that sense is also a special point. So, I mean, I think important is to realize that out of all the possible transition probabilities that I could draw from all these different states, here I'm only restricting them to a particular subset. That's sort of what makes it simpler in a birth and death process and will allow us to carry out the following derivation. So in my birth and death process, my transition probabilities, as I've said, are only between nearest neighbors. So if there is a birth event, I go from I to I plus 1. So those transitions are only to states in which I increase by 1 unit. If there is a death, my only transitions are between I and I minus 1. And of course, because time is ticking, is continuous, there are times in which I'm waiting in a given state. So that is I stay in I. And of course, as I need to have conservation of probability, as I've said earlier in my slides, the probability or the rate at which I am staying is 1 minus the rates which allow me to get out. So this is why you have to think in continuous time processes, that you have these waiting times at any given state, and then with certain probabilities you get out of them. So I've been, of course, saying this before, but lambda, I'll always use lambda for my birth rate, mu for my death rate, and of course I have to be careful from a sort of probability point of view. In principle, this is all you need, but there may be other terms that are less likely to happen. So, for example, I am ignoring here the possibility that every now and again, when you have a child, you don't have just the one, but maybe you have triplets or twins, right? So what I'm saying here is that those events can either be taken as two birth events separated by a small time interval, or less likely to happen. So given, as I've said, the nature of the transitions that can take place for a birth and death process, my Kolmogorov equations now become very simpler, much more simple, because out of, if you remember, let me just go up, so if you remember, this sum that I have here was over all potential states in my state space. But in the case of a birth and death process, if I want to understand what is the probability to be in a state n at time t plus delta t, the sum is only restricted to I can go to this state because I was in n-1 and there is a birth event, or I was in n+1 and there is a death event, or I just stay there. And of course, these other terms that come from the other states are negligible in comparison. So this is a much simpler, just because the structure of the transitions only connects you with one state to your right and one to your left. And of course, we need to be a bit more careful with what happens in cases for the state 0, and also if you have a population that is finite for state capital N. So what you can actually show, given this equation that I had just derived, the idea is that you want to take the limit in which your transition time, delta t, is sufficiently small. So in that case, you can rearrange the equation, and it can be written in this simple form. So as you can see here, what I have is the change in probability of state n between time t and time t plus delta t. And what you can see is that everything on the right-hand side only depends on the time t and birth rates for those states, lambda and the one to the right and one to the left. So doing things that probably you learned in high school, you get this differential equation, which is a differential equation, of course, linked to the other probability terms, right? But as I've said, once you've prescribed what your birth and death rates are going to be, it's just simple to solve. And I think it's important to point out that it's linear in the probabilities. So these are just first order ordinary differential equations with constant coefficients that only depend on the state. So with this, then, of course, sometimes you're interested in understanding what is the late time behavior of your process. So in the same way as you can think of a steady state in an ODE, an ordinary differential equation, you can think about what is a stationary probability distribution. And in this case, a probability distribution will be called stationary if the transition matrix times this probability distribution gives you back that probability distribution, in the sense that you're not evolving. Once you get there, you're stuck, so you're always there. And the question is, when can I have guaranteed that this probability distribution is going to exist? So there is a theorem here, and to me, again, these few theorems that I'm going to not prove but just show here are nice in the sense that they actually are proof of existence and uniqueness, but at the same time, they allow you to compute them. So in this case, in order to have a positive stationary distribution, you need to look at this infinite sum and see if it converges or not. And of course, what you see is that you have all the lambdas and all the mu's, so it's just a matter for your particular model that you're working with of looking at this infinite sum and understanding its convergence properties. And as I said, the theorem gives you more than that. It also gives you a way in which you can actually calculate what this final stationary distribution is going to be, again, in terms of the rates of birth and death in your model. So, I mean, I know this is sort of maybe too much to take, but very soon I'll just move to one particular example in which you can see this maybe with greater intuition. The proof is easier in the case when you have a finite number of states, but then there are times when you have special states in your system, and in this case, for me, special is an absorbing state. So what can we do in that case? So what is an absorbing state? So if lambda 0 is 0, remember that, of course, I can't get out of 0 to the left. I mean, if I have 0 cells, no cells can die. So, of course, mu 0 is 0. So if lambda 0 is 0, so for example, if I only have cells that I am not repeating from my culture, and I'm a very bad experimentalist and I'm not treating my cells properly, at some point, if in the culture they'll die. So if I don't have any migration, lambda 0, of course, if I have 0 cells, there's no way I can recover my culture. So I have an absorbing state at 0. So of course, eventually, with time ticking, where I'm going to end up is in a distribution in which all the weight is concentrated at 0. So what can you actually do? So of course, when you know that that's going to be the ultimate fate of the system. The question is, how can I compute that probability, and when will it be the case that that probability, if I wait long enough, is 1? When can I say that I have, with certainty, a probability of extinction equal to 1? So what are the conditions then for total population extinction in a general birth and death process? So again, it's a theorem that it gives you the answer, but also in a way that you can compute things. The nice thing, as I've said, is given you get your rates, you look at this infinite series, and in this case, the sum needs to actually be divergent. Very intuitively, you see for this to diverge, the numerator needs to be larger than the denominator. Sorry, the numerator needs to be larger than the denominator. So of course, the idea is that overall, your death events carry more weight than your proliferation events. That's when you end up becoming extinct. And in the case when this sum is actually convergent, you can actually calculate the probability of extinction. That, of course, will be smaller than 1, but it also tells you what is the probability, even if it's smaller than 1. So when you have guaranteed extinction, then the next question is, what is my time to extinction? Because there are some instances in which you may have, with probability 1, you end up becoming extinct, but the time to get there can be infinite. So what do I need to do? So for that, yet another little infinite sum. So the time to extinction is finite if this is true, and these are my formulae to compute the mean of my extinction time. So again, I mean, there, of course, I haven't shown this. One can actually show this. But to me, what I would like to convey today, more than the actual structure or proofs of every single step, is the fact that once you've defined your birth and death rates, all these times to extinctions, all these conditions to show that probability, I mean, extinction happens with probability 1 or not, and if probability of extinction is 1, what are the means for these times? Everything only depends on these lambdas. So once you have the lambdas, you can compute them. Of course, sometimes, most times, you cannot expect these formulae to give you closed forms for those times, but that's when you can have your computer and calculate this numerically. So something also important before I move on to the immunological example is to think about, I could have extinction guaranteed, I could think about the time to extinction, but what happens in the case when extinction may take longer than a given characteristic time scale for my system? So in that case, it's interesting to look at something that is not quite a probability, but it's a condition of probability. So I may ask myself before extinction takes place, what is the probability to have a given size in my population? That is a condition of probability. This means that I haven't become extinct. That happens with probability 1 minus P0. And the probability to have n cells is Pn. So these are conditional probabilities. They are not probabilities. And I can also, given that I had my Kolmogorov equations for the Pn's, and of course this Qn depends on Pn and P0, I can take a derivative and obtain an evolution, a time evolution, an ordinary differential equation for my conditional probabilities. So what I would like to highlight here is that they almost have the same structure as my Kolmogorov equations for my probabilities P's. So one, the Q's are conditional probabilities, number one. But then second, this term was there, this term was there, this term was there. But I pick up this new term, which comes from taking the derivative of P0 in the denominator. And as you can see, this is a nonlinear term. So these conditional probabilities satisfy a system of equations that is actually nonlinear, and of course our nonlinearity is going to make it more difficult to analyze from an analytical perspective, and it's important to see that that nonlinearity is related to mu1. Of course, that is there because what connects you to 0 from the rest of states is the rate at which you go from 1, which is the death rate from 1. So just for example, I've given this equation also because in this case now n1 is sort of the boundary of the state. So what one can actually do is think about this sort of quasi-probabilities in the sense as we were thinking of them with the P's. How do they behave in the late time? And this is where you have to be learning a bit more probability than I ever anticipated in my life. So with these things, you have to be careful that you have everything in place, and there is also different approaches you can take in the literature. So let me just give you two different distributions that sometimes they happen to be the same, but in principle they are not. So remember the equations that I just provided for these conditional probabilities. So I would say that a distribution is a quasi-stationary probability distribution if it is a solution to the previous equations where the time derivatives are set to 0. But I can also think about, if I let time ticking, what is the limit when I let time go to plus infinity of these conditional probabilities. So in principle, this may not be the same. And this limiting conditional probability is also a QSD, but I may have QSDs that are not limiting. I mean, the good news for us is that with the processes that we've been working, we don't have these problems, but there are very clever applied probabilities that have shown me that there are lots of counterexamples in which you can end up having different quasi-stationary probability distributions, but in a way that shouldn't surprise us, because in the same way as we have a variety, for example, of steady states from some nonlinear systems of ODEs, which of course, depending on where you start, you may end up in different states. So that's sort of a parallel concept here. So what I've said before, given this nonlinear term, solutions to this, either the quasi-stationary probability distribution or the limiting conditional distributions, are analytically harder to obtain. But Ingemann and Nassel develop a number of approximations, and two approximations that I would like to mention here are when the time scale of the death event from just the one single cell is very short, you can take the approximation that you set it to 0. And of course, setting mu1 to 0 in the previous equations already tells you that that term isn't there. So that will just take care of the nonlinear term. You just get rid of it. And of course, this is a good approximation when the mean time to extinction is long, because of course, if mu1 is 0 in a way, you never get to 0. Or what you could do is also replace the death rate from state n by the death rate from state n minus 1, which in a way, what you're saying is that as far as death is concerned, in every population, what I'm keeping is an immortal individual, right? Because the idea is that I have n individuals, but the death rate that I'm considering now is the death rate as if I had n minus 1. So you always allow one immortal individual, and in that sense, you can also do some computations. And this turns out to be a better approximation if the mean time to extinction is short. So with this, I will now move to the immunology for the next half hour. And what I plan to do is make use of some of these concepts that I've introduced here for an immunological problem. Do you have any questions before I move to that bit of the talk? No? Okay. So what is that I would like to talk to you about? So I guess on Monday we had great introductions to immunology, both by Binita, Satyajit, and I will not need to cover a lot of immunology. More than anything, I'm not an immunologist. But the idea is something that we are always thinking is if I have some T cell in the periphery, we're always thinking, right? The title of this workshop is Modeling Infectious Diseases. So this is this red arrow. I have whatever infection that will lead to T cell activation, a clonal expansion. After your clonal expansion, lots of cells will die, hopefully if you clear the infection, and you end up with memory T cells. But what I'm actually going to talk about is not this red arrow, but what happens when we are actually healthy, right? So hopefully we want to be here rather than here more often than not. So the question is, cells have a finite lifetime. They die with a certain rate. And in order to maintain your population of lymphocytes, which is very much required if you want to have a healthy immune system that is protecting you from any pathogens around, you need to have a bit of proliferation, so that's what I mean in this diagram compared to this clonal expansion that I have here, to balance my death. So that is called, in immunology, T-cell homeostasis. So this sort of balance between death and light proliferation events that take place in the absence of pathogenic challenge. So that is what I will be making a model of, this bit of the diagram. So I am actually not adhering to the instructions of the workshop. And of course, I think it's important for everybody to remember that T cells originate from stem cells in the bone marrow that migrate to the thymus where they develop. And then once they develop, those lucky ones that get out move to the periphery. And when I say periphery, remember it's the lymph nodes, blood, and spleen. So again, just a 1/2 second slide. Things start in the thymus for T cells. They start from precursors that we'll call thymocytes. And important there, as important in the periphery, is the interactions that they can mediate with antigen-presenting cells due to the T cell receptors that they express in their surface. I think it's important to maybe sometimes sit for a minute and really realize that immunology is really a beautiful example in which mathematics can really help you put things in pencil and paper and in computer. So even though I showed this picture, which in a way is sort of stationary, you see things happening, what happens in real life is that this is a process that is timed, well-timed and well-located. So it's really a problem of space and time where a cell happens to be at a given time instant. And you don't have all the time in the world to go through this process. You actually, per cell on average, you spend 2 weeks at most. 2 weeks if you're successful and you exit, less than that if you die in the process, which happens very often. So the idea is that you come in, you actually first explore the cortex, then if you actually, as I've said, you successfully get it to this other side of the thymus, you see other cells, and again, here you can either die or divide, and then you get out. And again, all this in about 2 weeks. And very little chance to pass, less than 5% chance to pass. And the idea is that depending on the types of signals that you may receive, you may, if you as a T cell don't get a signal through your T cell receptor, you're really not a good candidate to move to the periphery and survey, so you die by neglect. If you have a very strong signal, you may be a potential T cell that can lead to autoimmunity, recognizing household proteins far too well, and you die by apoptosis, or referred to as negative selection. And somehow, if the signal that you get through your T cell receptor is intermediate, you are sort of the lucky winner, and you get to be exported to the periphery and something called positive selection. So that's the immunology. So I think important to keep in mind is what is it that the immune system wants or requires to have. So we really cannot predict the precise nature of the pathogens that we're going to be encountering in the future. So how can you protect under such circumstances? So what I would say evolution has done in the case of T cells, so white blood cells that express the T cell receptor, is that you have a large number of cells of the order of 10 to the 11. And I'm only referring here to the population of T cells that is defined as naive. Naive in the sense that it hasn't seen antigen before. So as different from memory cells that, remember memory cells were the cells that I sort of end up have at the end of the immune challenge. So you have a large number of naive cells of the order of 10 to the 11 that can be actually distributed over a large number of different families, 10 to the 7, 10 to the 8, in mice, maybe 10 to the 6, that are characterized by the molecular structure of that T cell receptor. But then this is a large number of cells, 10 to the 11, that, as I've said, are in different types of clones. And of course, that means that they'll be able to survey antigens with different eyes. But when you have a large population that is heterogeneous, you want to ensure that, in a way, sort of you maximize diversity. And that type of competition is in place and furnished by professional cells that are antigen-presenting cells. And in this way, through this competition, what you can have guaranteed is coexistence and persistence. Unfortunately, as we age, both the size of this population and the diversity of the naive T-cell population goes down. And that means, of course, that if we lose some of these families, that means that at some point the family size went down to 0, so that would correspond mathematically to extinction. So it's in this context that I would like to then explore my immune mathematical model of birth and death processes. So this is an antigen-presenting cell, which can have peptide MHC in the context of only self, or if I have a bit of an infection, that's the red there. And just to remind you that every single cell has of the order of 30,000 T-cell receptors on its surface, but each T-cell has 30,000 copies of the identical molecular structure. So that is why I can classify my cells according to whether they have different colors of T-cell receptors. And of these different colors, as I've said, I have 10 to the 7 or so. And the idea is to actually, given this diversity and given the signals that they can get from antigen-presenting cells in the context of health, how can I model this? So what I would like to do now is maybe less important than the result itself are how you can formulate a model. So the idea is that I want to end up, I'm telling you where we want to end up, with a univariate Markov process, a birth and death process that takes place in the positive integers plus 0. And what I need to do for that is define my transition probabilities. I know that 0 will be an absorbing state. I am ignoring thymic export. As we age, the output of the thymus actually can be neglected. So if I don't have migration of new cells into my system, 0 would be an absorbing state. So what I would like to understand is various properties from a stochastic perspective of this process. But of course, this is what I want to get. And I'm going to show you sort of the hard work one needs to put in to get to this very simplified perspective. And of course, the question is this really, you put all this work to make something very simple, is it really worth it? So the good news, I will not show that today. That's sort of part of extra work. One can say that, yes, the simplified version can characterize the system more often than one would imagine. So let me then start with the model. So with the model, what I do here, so I have two types of elements. My T-cell chronotype, so each of these blue dots is a different family with a different T-cell receptor. I mean, they're all sort of identical. And let's suppose I'm interested in chronotype I. And in here, I'm looking at all the peptide MHC molecules that can be derived from my host proteins. And what I can do is ask my favorite immunologist, how can I draw links between peptides and chronotypes? And what I mean here by a link is in the context of not a pathogen environment, just self. Can I have a T-cell receptor that can see this particular peptide MHC so that if the T-cell and the antigen-presenting cell meet, there'll be just one round of cell division. So remember that seeing this will imply that this peptide will give a signal to this subset of cells to divide. So I could ask my immunologist to do this. So what I can do from a mathematical perspective is, given my I, my T-cell family, I look at Qi, which is the subset of all peptide MHC that can see that T-cell receptor. Now I can look at the diagram from the opposite perspective. I am a peptide who sees me, so I can do that. And if this is peptide Q, this subset of T-cell families will be CQ. But of course, the picture is always more complex than it is. So let's suppose that that is what my immunologists tell me. So from a perspective of I can see 3 different peptides. For the first one, it actually is sharing it also with this other clonotype. This second one isn't sharing with anybody, and the third one is actually shared with 2 other clonotypes. So the idea is that if I look at what is for this peptide, the competitors, it will be all the cells in clonotype I, but also all these other cells that I am not going to specify in greater detail, but I'll just say they are cells that compete with I and can see Q. So if I am aiming to get a mathematical model that can describe this population, what I would like to hope is that I can convince you that in order, as with this picture in mind, if I want to model I need to know what these other families are doing. So this will lead me to a multivariate Markov process, but that's rather complex to start with. So what can I do? What can I do to get rid of all this complexity? So just in colors, for that peptide that is seen by I, right, it sees Q1, Q2, Q3. For Q1, those are the TCRs that can see it. That is the competitor. For the second peptide, there's no competitors, and for the third one, I have 2 competitors. So ideally, what can I do about these competitors so that I sort of forget about what they're doing in such a way that I can model the evolution of my population of family I without them? So before I actually go to the simple model, one can actually say that you can get your computer and run the exact model. So from a bipartite graph of this type, you can go into the matrix of 1s and 0s, where I've put a 1 or a 0, depending on whether I have a link or not, between a certain peptide and a TCR, and I have 6 families of receptors and 8 families of peptides, so that is why it is 8 by 6. And what you can actually do is, if you have initial conditions for the population, so N1, N2, all the way up to N6, let's suppose that those were the initial numbers, you can formulate this birth and death process by help of a Gillespie algorithm. And my assumptions are going to be that death events are always linear and that all populations have the same death rate mu. So the total death rate in the system, given that at time t I have this many cells, will be just adding all the cells in the different subsets, multiplied time mu. And then how many birth events I'll have will be the sum of all the lambda rates. And how do I define my lambda rates in this model? So very simply, so if I look at population 1 sees 2 peptides, 1 and 3. It doesn't compete with 1. So the signal from, and sorry, that line shouldn't be thicker. And if it's thicker, it doesn't mean that it's stronger. So all the links have exact the same rate gamma. It's just that I didn't change that in my slides. So for peptide 1, there's no competition. I have 15 cells. So if that is the birth rate per cell and I have 15 and they get 15, then they're not competing with anyone. For the third peptide, N1 is also seen by N5. N5 has 11 cells. So 15 cells, but 15 plus 11 are competing. So that's the exact model. So I could put all this. And the idea is that running the time evolution of this system is nothing else but throwing your die every time. So the idea is that you have to throw your die, but you have to throw it twice. Remember, I talked about these waiting times. So the first thing I need to think about is, how long do I wait in a given state? So in my case, this is my state. Given that it's a Markov process, birth and death, the waiting times are exponentially distributed. So if I sample from a uniform distribution between 0 and 1, take the log, take the negative, and divide by the total rate. In this case, my die has 12 dimensions because I have 12 events, 6 death events and 6 death events and 6 birth events. So I throw my die for the waiting time, and then what I need to do is throw my die a second time to decide out of the 12 reactions which one. So for example, the birth in clonotype 1 will have this weight, and with the weights you sample and you move on. So this is one example of one such realization. I will not explain this because I want to move on. I only really have 10 minutes. But the idea is that you can write this down and look at the evolution. So what I'm plotting here just quickly is these clonotypes on the right-hand side turn black when they become extinct. So what you can see, if this is, I'm plotting, for example, here, two things. Number of clonotypes as a function of time. And what you can see is that very early on, I have a lot of extinction. So families are dying. The black dots were being generated. But then after some point, I hardly see any extinction events anymore. So that is sort of the quasi-stationary behavior. And if I also look at the mean number of cells per surviving clonotype, I can also see that somehow I'm reaching some steady state behavior. Something of interest that we would like to put more effort looking at is actually what is the distribution of clonal sizes. So I will not talk about that here, but that's also which is rather intriguing. So what do I need to do basically to push this competition problem to one in which can be handled just with the one dimension? So what you need to do is remember, I'm looking at my clonotype I, and I'm looking at one particular peptide that is being seen by I, so Q. Q can be seen by I, and my question now is, for that peptide, how many cells are competing for it? So of course, Q belongs to QI, so all the cells in I will compete. But then I'll also have all these other competitors. In principle, this number, this NIQ, cells that are seeing Q and are competing with I, could be 0 or positive if there's some competitors. So I have that this is really true. So this is my definition of my birth rate for clonotype, as I've done in the exact model. You look at all the Qs that can give a signal, and you take the rate of signaling and divide by all the cells that can see it. So what I'm going to assume, as I've said, is that all the links have the same strength. I'm in the context of self-peptide, so that's not a bad approximation. And I can write it like this. And I have a star here to remind myself that this birth rate for I really depends on these competitors. So in principle, the evolution of all my families are linked. So how can I sort of get rid of this competition in a way that I encode the competition, but I don't have to follow their time dynamics? So let's suppose that the clone I'm looking at is the blue one in this box. And every dot there is a peptide, MHC, that can be seen. So and all the other boxes are different clonotypes that are sharing. So this is like cows eating grass, and each cow has so maybe I'm the blue cow eating grass in my blue patch, and you have different cows eating grass in other places. So the question is that mathematically I can uniquely partition this set QI, all these dots are part of QI, by introducing this competition index R, and I can label my peptides that are not competing with anything else in yellow, so competition index 0, all the ones that are competing with just the one other clonotype, R equals 1 or 2, and I mean in this diagram I only went up to 3, but the idea is I'm going to forget whether this peptide is being shared with the green clonotype or this peptide is being shared by the purple. All that matters is that those peptides are shared with just the one other. In this context, what I want to do is what we call a mean field approximation, and sort of the rest of the clonotypes will behave as some sort of background. So this is the way you can formulate your partition, and now the sum that I have over Qs can be divided into I sum over competition index, and for a given competition index, I need to look at the Qs, the peptides that are giving signal to I and to R different clonotypes, no matter what the nature of those clonotypes are. So what I do is two things now. So I have to do sort of two hypotheses, simplifying hypotheses or conditions. The first one is to do what I tell my students not to do, that if you have a nonlinear function, the expectation value is not the value of the function. But anyhow, to a first, I mean, there are more terms here that I'm ignoring. So this expectation value goes inside. And then what I'm going to assume is that the average population size of all competitors is the same and given by this average n. So when I need to compute the average number of cells in this population, which is cells that compete with I for Q, but Q gives signals to R of them, I will have exactly R times average n number of cells, because it's our competitors, all of them with size n. So with this, I can actually write my birth and death, and the last thing I need to do is calculate the cardinality of the set, QIR. How many peptides do I have there? So what I can do there is nothing but just do a very simple binomial distribution. The probability to have sort of a competitor is this probability, and what you need to do is now you have, if your diversity of clonotypes is NC, I is fixed, so you have NC minus 1 different clonotypes. So what you need to do is I need to have choose R competitors. So with success, I have R competitors, 1 minus P, all these others that are not. And in the limit, which is this diversity, as I've said, is of the order of 10 to the 7. These probabilities of recognition are really, really low because there is a lot of cross-reactivity. So you can approximate the binomial distribution by a Poisson distribution. And we introduce this concept of nu. So quickly, I justify the approximation, but that's more or less intuitive to do because, as I've said, a given TCR can see of the order of 10 to the 6 different peptides, and peptides can be seen by many other families. So really, competition for one particular peptide with a given T-cell clonotype is really inconsequential, and what matters is that you're having lots of competition with lots of them, regardless of what is the specific nature of the one. So in this way, approximating my birth rates in this way, I go back to where I wanted. With this, at the time when we first derived this, we thought this is rather ugly. How much analytical work can we do? What I would like to say here is that so the death rate is linear, and the birth rate depends on these 3 parameters. So mu, remember the death per single T cell, and I have 3 parameters in my birth rate. Phi, which is the proliferation rate and is proportional to the number of peptides that can give a signal to the given clone. Nu is this average number of competitors, the niche, in a way, the resources available and competitors, and N is the average number of cells. And I put here in red this because all these other 3 parameters are really parameters for the given clonotype, whereas N is really a parameter that describes the rest of the population independent of the clonotype. So something that I will not show today, because my focus was to show the analytical work here, is that a posteriori you can show that, of course, this average N should come from a dynamical understanding of how the rest of the competitors do. So one can actually say that the regimes, particularly when you've reached this quasi-stationary behavior, in which this approximation gives you really the answer after all these events. So now, I mean, as I've said, these death rates are really ugly. So when we got ourselves thinking, can we now use of the machinery that I've introduced in the first half hour for extinction, can we actually show that extinction is certain with probability 1? So this is the infinite sum that one needs to analyze. So extinction is certain. And with the death rates you can do, I will not give the details. I mean, if someone is interested in the proof, I'll happy go through it. But the idea is that even though this is an infinite sum, you can actually see that these lambdas actually have an upper bound. And given that they have an upper bound, and the upper bound is actually phi, then the death rates are linear in n, whereas the birth rates have an upper bound, which is a constant. So you can always find a large n sufficiently large that the death rates will dominate the behavior of the system, and you don't run away to infinity. So that's sort of the nature of the understanding you need to have to ensure extinction happens with probability 1. So you can do that. You can also obtain equations for these average times to extinction with these A's and rho's defined this way, and you can compute these times to extinction. Again, given that extinction takes place with probability 1, if I wait long enough, my system will end up absorbed. So what can I say about the time evolution before extinction takes place? So remember, for that, I introduced these quasi-stationary probability distributions. And remember, they had this nonlinear term, and I defined what a quasi-stationary probability distribution was. So what one can actually do is, as I've said, they have this nonlinear term. So finding solutions for the ugly functions of lambda that we got was a nightmare. But one can actually do the approximation that Ingemar Nassel proposed. So first one, if the mu1 is very small, you can basically replace your original Markov process by this auxiliary one, in which, as you can see, I've removed 0. I've removed 0 because mu1 is 0, so I don't get out of 1. And you have this auxiliary process, which is just a normal process with birth and rates given by this. And you can compute these probability distributions with the theorem. And you can do a second approximation. In the case, maybe the times to extinction are not that short, which is to keep this immortal individual. And by keeping the immortal individual, of course, you also have an auxiliary process in which, as you can see, to get out of n plus 1 with a death, the rate is mu n. So I'm shifting it. And again, this is an ordinary Markov process. There's no absorbing states here, so you get a proper stationary distribution in that sense. And with pencil and paper, you can do that. And then from an immunological context, the parameter that makes a difference, a qualitative difference more than a quantitative difference, is this competition index nu. So you can classify clones according to how much competition they've got. Are they competing a lot or they're not competing a lot? And what we could see, of course, intuitively speaking, and the mathematics, that the clones that are going to die first are the ones that on average are competing more. So this would be here. And the ones that could stay are there. But of course, this is from a static perspective, which is what I'm doing. When you're doing the simulation, you really need to think that it's time dynamic, and you may be competing a lot, but if your other competitors die, then you become then hard niche. So what you can actually do is, in those two instances, either a lot of competition or little competition, the birth rates can be simplified and tractable analytically, and you can provide expressions for the distribution, the quasi-stationary distribution in both approximations with pencil and paper, and times to extinction as well. So I would really like to finish now saying thank you to Gautam and to Shitabra for putting this meeting together, the school and the conference. I think we're all learning a lot and really enjoying our time here. I would like to say thank you to Emily. She really pushed this forward. And maybe for the students, I would like to say that something that I really never imagined when I started doing immunology is that would force me to learn mathematics that I had never thought I would ever learn. So when someone tells you, and you hear it, well, but if you're doing mathematical biology, right, there's nothing new under the sun. And the truth is, it's not. We've talked now to a number of very good applied probabilists, and these questions of extinction, when you're dealing with multivariate processes, are really hard to study, so lots of mathematics to learn. I really would like to say thank you to Hugo, who a long time ago, when I randomly shifted to do immunology, he really had the patience to introduce me to all the immunology that I learned. And I guess he was coming from biology, doing mathematical immunology. I was coming from theoretical physics, doing mathematical immunology. And then Robin Callard, who unfortunately couldn't be here in this meeting, and Rob de Boer, because they've provided a lot of discussions that have really helped us understand this. Maybe take this opportunity, as I think one should, for DST and EPSRC coming to agreement. These things sometimes don't happen so often. So thank you to that. And with this, I'll finish and take any questions. Thank you.
Questions?
Jose.
In the interaction matrix between peptides, MHCs, and TCRs, you assume that all interactions are the same, no? What happens if you relax that?
Yeah. So this is something that we have done, and basically qualitatively, you don't change the behavior. Quantitatively, you change it a little bit. But the overall picture is that what really matters is how many competitors you've got. So if you think of this matrix, you need to look at, oops, God, I hate this. I mean, I'm so bad with these things. So on the right-hand side, you have the clones. So you always think of the clones first. I mean, I always come from a very biased T-cell perspective, not the antigen-presenting cells. So you think about the competitors, that's number one. But you also need to think about how many of these are being seen. And in the sort of which parameters matter most, the first one is how much you compete. Second is how much signal you get from this. So this could be true by having one of these links much stronger. And that really doesn't make a difference. So it makes a quantitative but not qualitative difference. So I mean, I can show you the specific. Something we've also done, I mean, if someone is interested, I'll mention it, is what happens here when you introduce thymic output. So in your birth and death process, you add a migration term. Of course, extinction is, so you have extinction at the clonotype level, but you don't have extinction at the population level. So what we're assuming is that you never generate a TCR that was already there, so you generate new clones. So what you do is you have to introduce two parameters. One, what is the rate at which you put a new TCR there? And of course, once you introduce the TCR, you give it the same rules as the others. So for example, to generate this matrix, what you do is with a certain probability P, you throw your die and you decide, you fix one TCR and you go through all these peptides and decide whether there's a link or not.